So, good afternoon, all. I think all of you enjoyed your lunch. It's okay.
Net op tijd.
Yes.
Sorry, daar goes your
Definitely everybody in this room knows Python. And how many of you know Ray? Oh, nice. That's good. And now it's time for Rob. He's a versatile data professional with experience ranging from data analysis to platform engineering and developer advocacy. Now he's a customer success engineer at Anyscale. He's here going to talk on the topic scaling Python to thousands of nodes with Ray. And the stage is yours, Rob.
Thank you. I'm mic'd up. And thank you all for being here today. Yeah, so as a kid, I used to read quite a lot. I'm not sure if you recognize this, but as you grow older, it tends to become a bit more of a chore to read. And I think about 2 years ago, I undertook the endeavor of reading the Wheel of Time series by Robert Jordan. Now, this series consists of 14 books and one prequel. And I'll be honest, it's quite the masterpiece, but it's also just way too damn long. There are nearly 3,000 named characters in there. And if it spans about 7 times Lord of the Rings or 4 times the Bible, you just can't really keep up with what's going on there. So while I really enjoy reading through this, it often ends up with me searching, oh God, who was that minor character again from 6 books ago? And the good thing is that, well, as a kid, I may have been more of a reader and would have been able to go through this more quickly and maybe remember a few more names of the characters. Nowadays, I have some other skills at my disposal. So, for example, if I want to look up the name of this character, who occurs throughout a few of the books, who is Stylen, I can just ask ChatGPT. That didn't used to be the case about 20 years ago. And the good thing is that it gives some sort of sensible answers. So she's the Queen of Altera and the head of House Mitsubar. And that gives me some pointers about the character that is in my current chapter. We also get some background and role details. And all of this is nice, but then, welcome. Then where it really starts to irk me a little bit is that the responses that I get are full of spoilers. So I've blurred them out here for those of you who might still be interested in reading all of this. But yeah, later during turmoil and political upheaval, major spoiler. And this isn't what I'm looking for when I just wanted to get a quick reminder of who that character was. So can we do better than this? And beyond just having ChatGPT at my disposal, I now also have some more data science and data engineering knowledge. So I thought maybe I can build something out of this. So what if we took this approach where we get a query, put it into an LLM and get a response? That's like the basic flow. What if we get all of our EPUBs, the books of Wheel of Time, embed them, put them in a vector database, and then we can retrieve those contexts and provide them to the LLM as extra context before generating the response. And the astute reader here in the room might recognize this as retrieval augmented generation or a RAG. This is about as much in depth as I will go into the machine learning part or the data science part of this, because truth be told, I'm a really shitty data scientist, and I only have surface level knowledge of what's going on here, but I do have quite a bit of knowledge about the underlying infrastructure that I want to tell you about now. So about me, my name is Wit-Liezenga. I am a freelance engineer, and nowadays I work as a customer success engineer for Anyscale. Anyscale are the creators of Ray. They're based in the US. I work here in Europe to service our European customers and help them get the most out of Ray and the Anyscale platform. Yeah, so I should say that Anyscale creates Ray. We also have a hosted SaaS platform. I will be showing it throughout a few of the slides, just to show you what's going on under the hood. But in principle, the demo that I'll be talking about is purely open source Ray. So you can run this on your own. I'll share the GitHub repository later on. And I already saw a few people taking pictures. The slides will be published on my website. So if you go to robdewit.nl, then you can find these there. So let's get to coding, the fun part. Imagine this is my computer, my laptop that's right over there, and I want to train that RAG that we discussed earlier. If I try to do that on my computer, something like this will happen. Like I'm also running Slack, I'm watching YouTube on the side. a laptop generally isn't enough to run very large AI workloads. So instead, what we want to do is we want to scale up from a single from a single machine to an entire cluster of nodes. And basically, and this is also why I visualize it as a box, a node is just a box. It's a server, probably somewhere in an AWS data center, or Google or Azure, whatever you prefer. And we want to go from that single box, that single computer that you can talk to and interact with, and scale up to an entire cluster of computers, which is what we tend to do if we are running large-scale AI workloads. Now, where it starts to become more difficult is when not all of these boxes are the same. They might be different, so we might have CPU or machines, GPU machines, nowadays TPU machines. And what can also be tricky is that some of these boxes might fail at any point, like a server may go offline, your node might get preempted. So if you're a cheapskate like me, you prefer to run on spot instances, and then AWS might say, oh yeah, we need that back because someone is willing to pay more. So you get evicted, and that's how you end up with a cluster that's no longer completely intact. All of this is to say that distributed computing turns out to be rather difficult. That was the case, still is. But the good thing is that as complexity in computing increases, we tend to develop new technologies to tackle those problems. So we invent new tech. And the piece of new tech, or new, it's been around for a few years, that I want to discuss today is Ray. So, very short history lesson. All the way back in the days of Methuselah, we used to have client-server architecture. So you had a CPU and you had a server, and that was easy to reason about and to program and get the results that you wanted. Now, when we moved to web services, we introduced another layer to that, which is virtual machines. Once we migrated to a microservice architecture, we had another layer on top of that, which is containers. So you can run multiple containers within the same VM. And now with large-scale AI workloads, where we have this heterogeneous compute underlaying it, so CPUs, GPUs, and TPUs, we need another abstraction layer on top of it, which is Ray. And Ray will help you manage the distributed computing throughout the entire cluster. And as it turns out, nowadays, if people talk about distributed computing, we're pretty much universally talking about AI. So, what does a Ray cluster actually look like? We have the physical boxes, like the servers and the data center, and I want to spin up a Ray cluster. My config might look like something like this. So I need a head node and a few worker nodes. My head node is an M5 2x large. I want some larger worker nodes, a minimum of 5 of those, and we can scale up to 10 if we really want to. I want these to be on demand, so I don't want them to get evicted because of spot reasons. And then I also want G5 X large nodes, which, if I recall correctly, are the GPU nodes here. And just to make sure I'm not continuously burning money, I want to terminate them if I haven't done anything for the past 2 hours. Just show of hands, who here has kept a server or a cluster running and racked up a few $100 AWS bill? Nobody? Yeah? Okay, yeah, there we go. Good. Yeah, it's a rite of passage. This helps prevent that. So once we define this cluster and we spin up the cluster, we get something like this. So these are the boxes again. We get the head node in blue, and these minimum 5 nodes, the M5 8x large boxes in green, yellow-greenish. And then as we start running a more intensive workload, we can spin this up further, up to the maximum cluster definition. This is basically what Ray lets you do. And then in the meantime, we can use Ray to orchestrate our workloads across that set of boxes, across the cluster. So what does that look like? We have a head node. On the head node, we have a driver process and a worker process. We have a Raylet, and the head node also has a global control store, which contains metadata for the entire cluster, and an autoscaler that scales up our cluster as needed. You don't need to worry about this too much. It's fundamental. It's in the docs if you really want to read it. I don't want to go too in depth right now. Then beyond the head node, we have worker nodes. All of those have driver processes as well, and also a Raylet. And typically within a Ray cluster, we, as workloads come in, we distribute them to the different worker nodes. You can run workloads on your head node as well. We generally advise against that. But yeah, that's as you scale up the workers, you can just do more stuff and you can do more compute. So at this point I want to dive into tasks and actors, because these are the fundamental parts of how array architecture works. So imagine we have this function. I hope it's slightly readable. Basically what we have is a list of items, or characters in this case. These are Wheel of Time characters, so rand, met, baron, etc. And we want to do something with that list. So we want to retrieve them one by one. And then we want to print the indices for the list. So rand is number 0, met is number 1, baron number 2, etc. To simulate like an actual workload happening, I've defined a time sleep here. So we will sleep for 10 seconds every time we retrieve a character. And if you do it like this, so we retrieve every index for every character. We're retrieving the index and the name. Then it'll do one at a time, and it will take about 10 seconds to retrieve them. So the total processing time for 5 characters is 50 seconds. That's rather slow. In this case, it might not matter that much, but if we want to do everything in sequence, you get a very long running pipeline. Now what we can do with Ray is that we start a Ray session, and we put this decorator on top of our function, so add Ray remote, and we make it a remote function. And then to iterate through the list, we can just retrieve the item remotely, and at this point Ray will spin up multiple tasks to get those indices. So in this case, we're down to approximately 10 seconds, because we'll execute all 5 of these in tandem at the same time, and then bring them back and provide the result. That's a RAID task. You can fire them off, they'll run, and they give something back, and you can't really interact with them in the meantime or beyond the lifetime of the task. Now, if you want to do something stateful, we can use classes, and that's where array actors come in. So here we have a class, ISADI, initialization stuff. We can retrieve some details about the ISADI, and we have a function to mutate the state of the object. So the ISADI can take 3 oaths, and this class will, or the object will keep track of that. If we turn this into Ray, then we once again only have to provide the add Ray remote decorator, and now these become Ray actors that we can distribute across the cluster and keep running and update their state, retrieve information from. So for example, what that looks like in practice, we initialize this ISADI, she's called Xuan, and we provide the initialization parameters. We can then say, okay, remotely have her take 3 of those oaths. So that's this function we defined right here. And then give us a result back. So all of this doesn't happen on your local machine, but on the nodes defined by your Ray cluster. So that's the basics of Ray explained. And basically anything that you do with Ray, you can reason down back to actors and tasks. Now, back to the RAG pipeline. So let's see what our basic setup looks like. So we have a query, and we provide it to the LLM and get a response back. I could do this live, but I won't right now. I've got it here in the slides and show you what we got back. So who's styling Quintara Mitsubar? This is, which model am I using again? Mistral 7B, latest version, if I recall correctly. So this is what we get back, and I'll need to read it here. It seems like you've provided a name in a fictional language, possibly from A Song of Ice and Fire by George R.R. Martin, as it resembles the Dothraki language, yada yada yada. Okay, so basically the LLM doesn't know about this very minor character in Wheel of Time. Strange. Still, I want to know more about it, so this is where the RAG comes in. This is our baseline performance that we're looking at. Now we do the embedding model, put the embeddings into the vector database, and provide that as context to our LLM. So basically I write a pipeline to process the EPUBs for Wheel of Time, and provide them in my question, the query, to the LLM. So what does that pipeline look like? First we want to download the EPUBs. I've uploaded them somewhere to an S3 bucket. Then we want to parse them, read their contents, chunk them into reasonably sized chunks, embed them, and write the embeddings to the vector database that we can then use later on in the RAG service. Now, If we do all of this in sequence, as I described before, with the 10-second delay, it will take quite long. But the good thing is that we can do this in a more streaming fashion and like parallelize this. So as the first EPUBs come in, we can start parsing them, and as their results come out, we can start chunking them, even while maybe the download EPUBs phase or stage is still running. And that's where array data comes in, which is one of the libraries for array. There are multiple of those. Today I'll mostly be talking about array data and array serve. So array data is built for streaming execution, as I described. So you can have data go through the first stage of a pipeline as another chunk of data goes through one of the later stages. And the core concepts here are data sets and blocks. And array data specifically is designed for large-scale AI workloads. So you can think about batch inferencing, data preprocessing, ingestion for ML training, or whatever you fancy. So these are data sets and blocks. Just to get a bit of a sense of what's going on inside of array data set, we have different chunks of blocks. So rows 1 to 1000 are in block 1, 1000 and 1 to 2000 are in block 2, etc. And those blocks have a number of rows and a schema. And then once we process through our pipeline, this is basically what streaming topology looks like. So we read our data, that's our entry point. Then we put it in a queue, and every queue has an in queue and an out queue. So every stage in our pipeline has stuff that it has generated and is waiting on the next stage. So, for example, the embedding creation or the embedding of the chunks, that takes a lot longer than simply loading them in. So you will build up a bit of a queue as data is waiting to be processed further. And at that point, like either you can just sit around and wait, or array will auto-scale the cluster, provide more GPUs, CPUs, whatever you need, memory maybe, so that you can process this quicker. And then in the end, we map operations to it, and we get an output. And that's our final data set, which we write to the vector database. Actually, this is the point where I might want to show what it looks like, not live, but at least when you run it on any scale. So the things I want to highlight here are that I launched this job to ingest data. As you can see, it starts with provisioning a head node, and then you get that head node. It pulls Ray into the server, the VM in this case. By the way, you can run Ray on Kubernetes or VMs, whichever you prefer. In this case, I'm running on VMs. And then we scale up the cluster. So attempting to add a cluster or add a node from 0 to 1. And eventually we upscale first to 16 CPUs, 1 GPU, and then 24 CPUs done 1 GPU. And eventually we scale back down again. And if we look at the array workloads dashboard, you can see that this is our pipeline. So we get input, we read it in binaries and split the blocks, then parse the EPUB content. We provide functions that basically chunk that content, embed them, and write them out. And this provides some insight. If I were to show you this live, then it would flow from downward to up. And while this one is finishing, this one might just get started. Eventually we write that to an S3 bucket somewhere, and now we have our embedding model used to store the stuff in our vector database, and we can start retrieving those contexts. This is what our rec looks like. Nice. Now we need to access it somehow, and that's where array serve comes in. So we can use array serve to run our class or actors as an approachable service that we can access through an HTTP or HTTPS endpoint. So basically you can just go to a link or curl something and get a response back. I'll show that in a little bit. The nice thing about array serve is that we can once again scale up the cluster as we need it. So if I provided all of you with the URL in a little bit and we all started querying the service, then it would provision more nodes and use more compute to answer our requests. And array serve in particular is very well suited for model composition, where you want to run multiple models alongside one another, and or serve and aggregate their responses. And the core concepts in array-serve are deployments and replicas. So basically, deployments contain multiple replicas, and replicas map roughly to array actor. So the ICDI class we saw earlier, that would be something that is contained in a replica here. I can show this in a little bit. What does it look like in practice? We have our deployment here, or rather multiple deployments. We deploy a query encoder, a vector store, a retriever, the LLM client, the QA service itself, and that's the main engine that we will be talking to if we run a query. So what does it do? As you can see here, we combine retrieval and generation and send it to the pipeline. So we retrieve relevant context using the retriever, and that's from the vector database. That's the EPUBs that we have parsed previously. We then augment our original query, and the query is who is Thailand or who is Rand or what happens in book 1. We augment that with the data that we get from our ebooks, and we then use the LLM client to generate a response. And we can format it and provide sources as well so that you can look it up where stuff actually happened. And then we use Fast API to wrap this and provide an HTTP endpoint. And the last one is probably not worth mentioning. So, how do we do? Who's styling Kitara Mitsubar? I don't know. And this is the point where we find out that, as I said before, I'm a lousy data scientist because I haven't done anything with the RAG part itself. We were just looking at the infrastructure. But luckily nowadays we can use Claude or ChatGPT or whatever to actually improve our pipeline. Or rely on our trustworthy colleagues, which is helpful in my case. So I hope we can do a little bit better than here. And what is actually happening is that it's just not retrieving enough context to answer our questions in a satisfactory manner. And we can see that here with Randall 4, who is the main character of the series. So the base LLM knows, oh yeah, he's a character in the book series The Wheel of Time by Robert Jordan. Okay, we get that much. He's the son of Odin and the heir to the throne of Asgard. We're now doing Norse mythology at some point. So yeah, this doesn't help us read through the books any better. Whoops. What can we do? We can start fiddling around, so we can increase our chunk size. We can increase the overlap between chunks. And we can increase the number of the number of chunks that we retrieve when answering our question, and that way we provide more context to the LLM to give us a better answer back. So how about now? Now we've done this. Again, Thailand. She's queen of Abu Dhar and the mother of Beslan. She's described as beautiful woman. Has anyone here read the books? Yeah, good. Okay. What do you think? Is this accurate thus far? Beautiful woman with long black hair and sharp eyes. Also possessive of Matt Cawthon, and she wants to marry him. Powerful figure in the story, and she has a significant impact on the events that unfold. Okay. How about in the back? Does this sound accurate? Okay, so this is the problem that you run into when reading Wheel of Time, right? It's been a while, and you really have no idea what's going on. I can tell you from experience, this is vaguely accurate, not accurate enough in some places, and also hallucinating a few things. I wouldn't say she has a significant impact on the events, and also doesn't really tell me what's going on. So we can do one more step to make this any better. So it is already better, but we want to do some more stuff. So first of all, the step I took here was get a newer Mistral model that allows for a larger context. And then we also added a re-ranker to select the best chunks instead of the closest ones. And yeah, augment our response in that way. So this way we get our max context up to about 60 pages. It's a bit difficult in EPUBs to translate tokens into however many pages are in a novel. But yeah, this is where we are right now, and this is the service I've running. Should I show this? No, let's actually do this one live. We've got 5 minutes and a bit, so I think we can just do one. So we have the LLM service here that runs our basic LLM, which is Mistral, and it's got a router and the LLM server. And then here's the QA service that we deployed previously. So we've got a re-ranker, LLM clients, vector store QA, query encoder, retriever, and QA gateway. honestly, if I start listing stuff like this, I barely make sense to myself anymore. So please don't follow along as we go here. Yeah, we can show this. Actually, let's zoom in. Maybe a bit too much. Okay, so we can run our script. UV run main.py query. Who is styling? Actually, let's, for the sake of time, not retrieve too much. Can we collapse this? Nice. So as you can see here, oh, sorry about that. We query this, the service is going on over here, and then we can go back to the service, the reg, and we should see here somewhere in the logs that this query came in. So it's now processing and generating a response. And there we go, it's come in. So, who's Thailand? She is Queen of Altara in the city of Abidar, that's correct. Flowing hair, honestly no idea. She begins laggering the first 2 fingernails on each hand. Actually that happens halfway through the books at the point where I am. So that's good. She is married, but I believe her husband has died. It doesn't show that. Sons and daughters, makes sense. Yada yada yada. Fondness for lace on a man. Actually, yeah, important plot point. And she has a liking for Matt's bottom. These are not my words. These are Robert Jordan's words. She's also known for her flirtations and assertive behavior. That's definitely true. I wouldn't say she's friends with Surf and Toon, but it sort of checks out. And they spend a lot of time together. Okay. She's also the one who sends Matt summonses. That's hardly a word. By having him find her knife stuck in the bedpost. Actually, that happened as well. So we are getting to a reasonable output, which is roughly what I wanted from this project. And it doesn't provide me with any more spoilers for the rest of the series. So, great success. Woo! We did it. Takeaways, or conclusions, if you will. What can we use Ray for? We can use Ray to orchestrate AI workloads across very large distributed clusters. And the great thing here is that we can use different sorts of compute, and our boxes, as I showed them before, don't need to look the same. The basics for Ray are tasks and actors. Tasks we can just fire off and forget about until they provide something back. Actors are something we can come back to with state and keep interacting with. Specifically for this use case, Ray Data and Ray Serve are dedicated libraries that help us set up pipelines like this. So first processing data and then actually serving it and getting something back from it. And finally, for the Wheel of Time, I would say it's a masterpiece, but also it has some very problematic pacing issues, especially between books, I want to say 8 and 11, and just way too many characters. Thank you all for being here, for your attention, and if there are any questions. Sorry, one more thing. Like I said, I will publish the slides on my website, but if you do want to look at the code, it's on my GitHub. My handle is rc_de_wit. I'll leave this up, and then you can look at the code itself and run it yourself.
Thank you, Rob. Any questions from the audience? Oh, yes.
Thanks, Rob. Very fun project. I'm still wondering, how do you prevent it from getting spoilers?
Yeah, very astute question. That's something I sort of glossed over. So actually the ingestion for this project doesn't take that long. I think I can process in about 20 minutes, quicker if I spin up the cluster faster. So what I've been doing thus far is just removing the EPUBs that I haven't read yet. So I still have 2 to go. So I can just run the ingestion with the first 12 books, and then I don't get spoiled that way. There are probably
Smart.
cleverer ways to do this.
Thanks. You have a question?
Yes, thank you for the insightful talk. I was wondering, is Ray also open source and free to use,
Yep,
or and it has an enterprise layer that's paid,
Yeah.
of course?
Sorry if I didn't address that clearly enough. So Ray itself is completely open source. So go to Ray.io and ignore this button, and then you can like run it yourself. And here I can also show it on GitHub. So the difficult thing with Ray that you still need to worry about if you run it open source is how do you get the actual compute? How do you run a cluster? So you can actually spin up a cluster right on your laptop and simulate one. You can also provide it with credentials to spin up VMs on AWS, for example, or you can use Kubernetes if you're already using that. So especially for the open source side of things, if you want to use Kubernetes, there's another project called KubeRay, where you can use pods as Ray nodes.
Yes. Thank you, Rob, and thanks for the absolute mind-blowing talk.
Wouldn't go that far, but thank you. If there are any further follow-up questions, I'll hang around here for a little bit so we can chat.
And now we have a break for 5 minutes, and the next talk begins by 1:25.
Thank you.